So we're going to start off in Maple on this one. Just to verify, I just typed in desolve, and I'm desolving the initial value problem from the last example. And this is just the differential equation, comma, the initial condition, and I put it inside the brackets to let it know that it is an initial value problem, both the differential equation and the initial condition. And sure enough, Maple tells me that I get the exact same answer that we just found, which is really, really nice. And then the other thing that I did was I typed in the code that's in the notes for the initial value problem with a bunch of other initial conditions, just so that we could see what happens. And if you look at the slope field for this one, and all I'm doing is I'm looking at positive values of t, I see some interesting things happen. If I back this off, if I change this to go from -8 to +8, then we wind up with a really crazy looking hectic mess, and some of my solution curves kind of disappear. They take off and they fly off the screen. But really what I want to do is I want to focus on what's happening with t values from 0 to 8, just so you can see those initial conditions that are all kind of in the middle here. They're all starting in the middle along the y-axis. But as time goes by, every single one of those initial conditions kind of falls into line, and it looks like they all sort of follow the same general curve. Now, because of the initial value, or excuse me, the existence and uniqueness theorem, we know that those curves can't become the same curve. They don't actually become one curve. They just get infinitely close to each other. And this is really useful because those initial conditions started off radically different, right? These are all in different places, but yet very quickly as t goes by, you wind up all the solution curves just seem to follow the same pattern. And as a matter of fact, if I were to add one more initial condition into this mix, let's say I'm going to make an initial condition like right here at t equals 2 and y equals 0. So y of 2 equals 0. Then I'm going to have to add one more color to it. So let me give this one a color, I don't know, red, just for flair here. Take a look at what happens to that solution curve. If my initial condition's right there, I mean before it had a curve as well, but quickly it falls into line with all the others, right? And it seems like no matter what, no matter where I start on the slope field, I wind up heading to the same curve, which is exactly the point that we're going to make here in the notes. So switching back over to the notes, once we play with it on Maple, we find out that all those initial conditions, they matter for small values of t. And so on this side, we can see that the initial conditions matter when t is small, right? So when t is small, close to 0, it matters where you start. But as time goes by, everything seems to kind of fall into the same shape, right? Fall into the same curve. The argument that we could say is as t approaches infinity, and it doesn't even have to go that far, all solutions converge on the same shaped curve. And I don't know if you noticed, but it's kind of sinusoidal. It looks kind of like a sine curve. But remember my general solution for this from the previous page, and I'm going to have to flip my notes back over to remind myself what the general solution was for this. It was y of t equals some constant times e to the minus 3t. And then there were those two terms with the crazy fractions, 3/13 times the cosine of 2t plus 2/13 times the sine of 2t. Now, if you look at that solution, that general solution carefully, you'll notice that as time goes by, as t approaches infinity, what happens to this term right here? As t approaches infinity, the entire term right here goes to 0. And so as t approaches infinity, this thing goes away and you're left with a solution curve that looks like this. These two guys don't head to infinity. They don't head to 0. They just kind of flip-flop back and forth. They wibble-wobble between maximum and minimum values. This is the shape that we expect. That, my friends, is the long-term behavior, right? This behavior right here is coming from those two terms right there. And so down at the bottom, we've got some text to be able to kind of fill in. Please notice that it says, before too long, every solution curve behaves like the periodic particular portion of the solution. This was y sub p of t. And because of this, we're going to define some things. We're going to refer to the kind of early days over here on the left as sort of the transient solution. The homogeneous case is really what we call the transient, or sometimes it's referred to as the natural solution. That's the portion of the solution that comes from the homogeneous case. It goes away. In this case, it goes to 0. It matters less and less. And then below that, you'll notice the portion of the solution that was the particular solution of the non-homogeneous case. That's what we call the steady state solution. There's a couple of different names for it, but steady state solution gets used a lot in engineering and science. And this is what matters as t approaches infinity. Right? It matters in the long run. And remember, when you hear that phrase or you see that phrase, they're making a limit argument. As t approaches infinity, blah, blah, blah. In the long run, that's all the same thing. That's all the same kind of long-term argument. So we've seen how to kind of make a sense of this on Maple. Now we've got one more example that we're going to do of just a find the general solution problem. And then there's also one more example at the end of this section that's all about application. So on the next page, we have find the general solution for the following equation. Now this is a classic example of the 3 steps to follow. Step 1, you're going to find y sub h. Step 2, you're going to find y sub p. And step 3, you're going to combine. So take a second. I want you to hit pause and try this, right? You can grab a blank sheet of notepaper or grab a whiteboard and scribble it out and see if you can do these 3 steps just on your own without watching. So make sure you hit pause and give it a try right now. Okay, so hopefully you've had a chance to try it. We're going to jump right into it, find the y sub h. And if you remember, y sub h is pretty easy for us because it's messing around with only the homogeneous portion. And as the previous ones have been, this is really just a exponential decay. So we know y sub h is equal to a constant times e to the minus 4t. Again, if you've done enough of these, then you can see and jump right to that. And I'm totally fine with that. But if you're not seeing how we got from here to here, you just need to practice a little bit more, and that's okay. Step 2, if you remember, was find y sub p. And for this one, we have to be able to write our equation and then kind of organize our thinking into a guess. And so just a reminder, we had dy dt. And I'm going to move my 4y to the other side because I get to go my y's to the same side. And the reason we do that, honestly, is because it makes it easier to look at this and go, okay, I'm going to take something's derivative, add it to 4 times itself, and get something that's like an exponential. And so off to the side, you're like, okay, I think I've seen this before. This is going to be another exponential. And the power, the upstairs for the exponential is just going to be negative t. So my guess has to be something that makes sense with respect to that. So I'm going to guess y of t is equal to some constant a times e to the minus t. Now notice I didn't say 9a. I just said a because I don't think there's any reason to believe that it's 9 times something. But let's see what we get. If that's the case, then I know y prime of t is equal to negative a e to the negative t. And so we can grab this and then throw it in and see what we get. So we're going to take our first derivative, which we know is negative a e to the negative t, plus 4 times the guess itself, which we know is a e to the negative t, and that's all got to be equal to 9e to the minus t. So a little bit of simplification, I have minus a plus 4a, so this is 3a e to the minus t equals 9e to the minus t. Now the nice thing about exponential e to the t is it can't equal 0. So if I divide both sides by e to the negative t, I don't have to worry about dividing by 0. So I can just kind of cross these out and say I'm going to divide those out. I don't lose any clarity for my solution. I don't lose any solutions. So really my equation turns out to be 3a equals 9, or a equals 3. So that means that my particular solution for this solving process is going to be 3e to the minus t. So I now have my general solution for the homogeneous part. I now have my particular solution for the entire thing, and so step 3 is just combine. Or combine, depending on where you grew up. So we're going to put them all together, and we will have our overall general solution, which would be y of t equals this guy right here, c e to the minus 4t, plus this guy right here, 3e to the minus t. And that's my general solution. Now, of course, we can check it, just like we should always check our answers. And you can check it on Maple, or you can check by taking this and substituting it back into your differential equation to verify. Now, again, I don't want to take time on a video to do the verification step, but it's super important to do that, especially like on problem sets and exams. You definitely want to verify your solutions. So we'll stop here, and in the last video we'll do the application problem that remains.